So we're going to talk about things that affect free energy, Gibbs free energy. So things that affect Gibbs free energy include temperature, pressure, we'll just make a pi sign for pressure, pH, and then concentration of reactants and the concentration of products. So what I want to do in this video is take a look at the effect of temperature, so the effect of temperature and the effect of the concentration of reactants and products. And things like pH and pressure, pH specifically we'll deal with in a later video. So because being able to calculate delta G is affected by the things like the concentration of the reactants and products, it would be pointless if we just said that the change of free energy for a specific reaction is, let's say, is -5 if the pressure is X and the pH is Y and the reaction product concentration is Z and the temperature is something else. So it would be much better as if we could say if we had one formula that we could calculate and determine what the Gibbs free energy would be at any given variable situation. And so what chemists and thermodynamicists have done is they've defined what's called a standard state. So delta G with a little degree sign above it is called delta G naught, is also called delta G standard state or standard state free energy. And the way you can calculate delta G under any given product and reactant concentration and any given temperature combination is if you know what delta G, so delta G is equal to delta G in that standard state plus the gas law constant times the temperature times the natural log, so that's Ln, of the product quotient. And if you remember, the product quotient or the reaction quotient is equal to the concentration, so we'll put the concentration of C times the concentration of D over the concentration of A times the concentration of B. And so by A, B, C, and D, I mean that if we had a reaction of A plus B yields C plus D, then our reaction quotient is equal to the concentration of the products over the concentration of the reactants. So we can take into account the temperature and the concentration of both products and reactants and find out what the free energy change will be. But what is this delta G standard state? Well, the standard as so delta G standard state is defined as, for solutions, it's 1 molar concentration, and for acids, it's 1 molar hydrogen ion concentration, which is equal to a pH of 0. So if you have an acid, pH of 0 is standard state. Typically pressure is equal to 1 atmosphere for standard state. So they set up all of the chemists have taken all of the conditions that can affect the spontaneity of a reaction, and they have said these under this specific conditions is our standard state. And then you can go about and figuring out what delta G is under those exact given conditions for that reaction. And once that is known, you can solve for the delta G by adjusting variables like the product concentration or the reactant concentration and those kind of things. So let's go back real quick and talk about our number Q, our reaction quotient. Q we said was equal to the concentration of C times the concentration of D over the concentration of A times the concentration of B. Now, when this comes to equilibrium, then we call it KEQ, right? So Q equals KEQ whenever the reaction is at equilibrium. Another interesting thing is whenever a reaction is at equilibrium, there is no net forward movement and there is no net backwards movement. So that would mean that, so whenever we know when delta G is less than 0, there's forward movement. When delta G is greater than 0, then there's backward movement. So in order to be no net forward movement and no net backward movement, delta G would equal 0. So delta G would equal 0 whenever the reaction is at equilibrium. So let's take our equation. Delta G is equal to delta G standard state times, or rather plus the gas law constant times the temperature times the natural log of Q. And then let's set our reaction at equilibrium. So let's say that the natural log of Q is equal to the natural log of H, or the natural log of KEQ. So that would make delta G 0. So delta G would equal 0, delta G standard state, plus RT natural log of KEQ. So KEQ. So now if we know what the equilibrium constant is, then we can calculate. So if we know what the equilibrium constant is, we can calculate what delta G standard state is, because we could subtract this over. So negative delta G standard state is equal to RT natural log of KEQ, right? So we would just change that up. So delta G standard state is equal to negative RT natural log of the equilibrium constant. So I can find the standard state free energy change of any reaction if I know what the temperature of the reaction is and I know the equilibrium, the reaction quotient, the KEQ of that reaction at that given temperature. A lot of people don't like to work with natural logs, so you can actually convert it to a base 10 log, which is easy to do. You simply set log base 10 of KEQ divided by log base 10 of E. And what you end up getting is that delta G standard state, if you want to put it in terms of the log of base 10, is equal to negative 2.3 RT over log of K, or times the log of KEQ. A lot of times people do this because log 10 is easier to calculate and easier to think about without a calculator. But with a calculator, it doesn't make a difference which one you use, and I think that this is just a little bit easier to remember because you don't have to remember an extra constant. Now the other thing is this works both ways, so I'm going to go ahead and scratch this out because I don't use this. I use the natural log. If you did use this, you can. That's fine. But this works both ways. You can solve delta G by knowing the equilibrium constant, but you can also solve the equilibrium constant if you know delta G standard state. So KEQ is equal to E raised to the power of negative G divided by RT. So this is all a power of E. So that's delta G standard state. Or if you like to use log base 10, then KEQ is equal to 10 to the negative delta G standard state divided by 2.3 RT. Now if you've never seen E before, you maybe skipped that day in your algebra class, E is equal to approximately 2.7.